Next, we have Jennifer Pett-Ridge. And Jennifer is the lead author of the Roads to Removal and distinguished member of the technical staff at Lawrence Livermore National Lab. Her leadership on this effort is just significant. The report includes a 68-member team, or maybe it's even higher than that. Lots of DOE national labs, not just Livermore, lots of academics, even including my team at Penn, but lots of academics. And the analysis, if you haven't had a chance to really dig in, you should. It's a county-level assessment of carbon dioxide removal approaches across the United States and really drives down community impacts, opportunities, and that every region has a unique set of solutions but opportunities. So, Jen, thanks for being here.
Hi, everyone. I'm thrilled to be here. And I have to tell you, I grew up in Pittsburgh, Pennsylvania, so this is close to my home. This is my home state. And so I'm going to give you a little bit of a high-level overview of a really very weighty report that I can really only start to grab little pieces, but I'll do my best to tell you the pieces that are particularly relevant for Pennsylvania. But I also want to, again, credit the wonderful authors who came not just from Lawrence Livermore, but from Penn and from universities and other national labs across the country. We have a large contingent from Livermore today. Yes, we did put a lot of CO2 in the atmosphere, but I want you to make that worth it by engaging with these folks who are the subject matter experts. If you see Lawrence Livermore on somebody's name tag, ask them what they wrote, which were their figures, what did they find in their analysis, because you will learn the real heart of gold in this report from the individuals who are here in the room. So I also want to share another sort of personal story, for me at least, and just reminding us why we're here.
As a scientist, I know by the time she takes her first breath, 9 billion more tons of carbon pollution will be in the air. When she takes her first steps, wildfires will have burned millions more acres she could have explored. The day she gets her first pet, there are thousands of newly extinct species she'll never meet. The night she forgets to call, the night of her first heartbreak. Her future home floods for the first of many times. By the time a child born today goes to college, it may be too late to leave them the world we promised. Our window to act on climate change is like watching them grow up. We blink and we miss it.
So I just dropped my eldest off at college. I also just celebrated the first birthday of my step-grandchild. So that feels very personal to me. But the story that you see on the screen there, that later is too late, is what I want you to take away. We're not talking about something that is 5, 10, or many decades in the future. We're talking about something that we needed to do yesterday and that we have to do today and tomorrow. So please also keep that in mind as we go through our conversations today about what we can do now and not just what we're preparing to do. You've probably seen a figure like this many, many times. We know the first answer is decarbonization. We also, Jen explained well, the second answer, and really interdigitated within decarbonization, is carbon dioxide removal. We can't wait. It's not one or the other. We can hold two thoughts in our head. And that was made very clear both by the IPCC and the Biden administration. So when we set out to write this report, what magic number did we pick? Well, we decided to go with what the Biden administration had put out there as the lead, and also that the Earthshot program, which Secretary Granholm recently stood up, identified as our goal, which is 1 billion tons or a gigaton. Is that enough? Probably not. But that is a number that we essentially asked in this report, can we achieve? And why did we write this report? Well, it actually took a little bit of backstory to tell you, but that we, in the state of California, where I am currently reside, where our governor essentially set out the goal of being net zero by 2045. And we were asked some years ago to figure out, is that achievable and what will it cost? And so many of you in the room actually contributed to what we sometimes call the California report, or getting to neutral, where we showed that, yes, we can do it. We can afford it. And we figured if we can do it for one state, let's do it for all of them. Let's do one better. Let's do county level analysis so we can provide really high resolution data to the folks who really need it. And so that's what roads to removal is. It's an assessment of capacity and costs. It's not an integrated assessment model. It really takes the existing resources that we know to exist in terms of technology and where forests are and where agriculture is and water and land and people, et cetera, and calculates what is possible. So as Jen mentioned, it took a huge team, over 60 authors. They come from all across the US. We really tried to make this as unvarnished, as unbiased as possible. It's not meant to be a policy wagging your fingers kind of document. Of course, there are policy implications, and I want you to think about those, but it really lays out the data. And if you want to work with that data, you are most welcome to, and I encourage you to look at that website, roads2removal.org. You will find interactive maps. You will find wonderful little videos that you can show your mom. You can find all sorts of things that are useful in integrating this knowledge in the classroom and in the policy arena and et cetera. But I want to also make it very clear that what we took was data that existed now 2.5 years ago. This needs to be a living conversation. We focused on technologies that were mature then. The technology has already evolved. But let me tell you a little about what the technologies we did look at. So removal pathways where we're starting with carbon dioxide in the air. The OG of CDR are plants. You know that, right? Photosynthesis is the best way to pull that CO2 from the atmosphere, and plants do it without thinking about it. We grow plants, we grow forests, in many cases on purpose. We're doing agriculture on something like 40% of the terrestrial land surface. So that's an opportunity because a lot of that biomass that we grow for food and fuel and fiber, we actually then allow to decompose and it's re-released back to the atmosphere. A little of it gets stored in soils through roots and activities of microbes. But that organismal decomposition that happens go back to the atmosphere could be interrupted. We could either encourage more of that carbon to end up in the soil or in the tree biomass, or we could collect some of that biomass and use it for other purposes. Now, when some of you are thinking about these ecological storage solutions, you might think, oh, this is not very permanent. But let me just tell you that my colleague Allegra has shown that renting that storage that may be impermanent and only last for 20 years is still very, very important for the climate system and helps build a bridge for us to buy the long-term storage that might gain through techniques like BiCRS or direct air capture. So let me tell you about those. BiCRS, or biomass carbon removal and storage, is essentially collecting that biomass that would otherwise decompose, whether it's from municipal waste, what's in your green bin, whether it's from forestry or agricultural residues, or even purposely planted carbon crops. And we were very careful not to displace any food crops or fuel crops. Sorry, food or fiber crops, but only on marginal lands or places where we don't necessarily need crops to be feeding the populace. So that biomass can be used to make lots of different wonderful products. I'll talk more about that in a moment. But the key thing to focus on is actually not the products. It's on the capturing of carbon and then storing it in some relatively permanent way, whether that's in a geologic reservoir or in some sort of other long-lived product. And lastly, we've shown, and many others know well, that we are going to need direct air capture or removal of CO2 from ambient atmospheric concentrations. And most of you are very familiar with that concept, but I just want to emphasize that what we're talking about here today is not only storage in geologic reservoirs, but also in building materials, which may be a more short-term solution for where to put that CO2. Again, I want to emphasize we only looked at mature technologies. You probably are thinking, where's the mineralization? Where's the enhanced rock weathering? Where's my favorite R&D technology? That's coming. But again, I want us to think about what can we do today? So skipping to the answer is yes. We can absolutely hit the target of 1 billion tons of removals. We could probably even do more by the year 2050. Now, what will it cost? $129 billion per year. I always like to look into the eyes of my audience and get a sense of, do they think that's a big number or a little number? This is waste management of invisible garbage. Do you want to pay that much money? What's the counterfactual? Well, let me give you a couple of numbers. One is that that value is less than 1% of our current GDP. We currently spend something close to 5% of our GDP on the health effects from oil and gas, from fossil fuel use. We're spending something upwards of $90 billion a year on just the damage that's done from climate effects, the big disasters. That's what NOAA tells us. And that's just in this country. So I actually think that's a really reasonable number. What else, what other commodity can you buy for $130 a ton? Rocks, sand, not much. It's really a bargain. And the jobs that come with this and the transformation of our economy, I think, is a healthy direction that our country can go in. And in many cases, it's helping to improve the lives of individuals in communities that have disproportionately lost jobs because of transitions out of fossil fuel economy. But this is the message again. We have to act now. We really have lost the position where we can wait for the perfect technology, wait for fusion, wait for the best single solution. We need to think about all these solutions, and both forests and soils, which are the green bars at the bottom there, which per year do not have enormous removals, but can literally start tomorrow. Those are things that we need to incentivize immediately while we are ramping up our ability to do biomass capture, to do direct air capture and use it and store it, that CO2. So each of these technologies that I talked about has different costs. The lowest cost, you can actually make money through doing productive production forestry, especially if you're in the southeast of the US. But it's very, very low cost to put carbon into forests and soils. The costs are more in the $100 a ton range if we're talking about biomass carbon capture, especially if we're converting it to hydrogen through gasification. If we need to make sustainable airline fuel, there's a bit of a premium there, and we're up near something around $150 a ton. If we're doing direct air capture, what we project by 2050 is the cost will be somewhere in the range upwards of $200 a ton. That is more than we'd ideally like to spend, and that's certainly less than we are currently spending on direct air capture. But we're fairly confident that we'll be able to get to that point. All told, this is essentially showing us the package of approaches, the lowest cost package that would get us to 1 billion tons of removals. Now, this figure could extend far, far to the right. It would get us to something like 14 billion tons of removals per year, all with direct air capture. If we decided that was the way to go, I would suggest that we start with some of these other opportunities that are lower cost. So let me walk you through some of them. I'm going to start with agriculture. This is my comfort zone. I'll tell you, I'm trained as a soil scientist as well as a forester. But this is a slide that I've taken from my good friend Jane Zelkova, that agricultural systems both contribute to climate change through the release of methane, nitrous oxide, CO2, but also are opportunities for mitigation. And what we looked at were the techniques that are known to remove carbon. If you know that soil carbon is impermanent, what you should also know is that we've lost something on the order of 500 billion tons of carbon from our soils in the last 100 years. It's an enormous amount lost. It's an enormous opportunity to regain. It's reversing the Dust Bowl. It's taking all of those agricultural lands that we've intensively managed to grow corn, which we then turn into ethanol that we put in our tank, to think about other ways to use those resources. And some of these simple technologies that we can act on right away, like cover cropping, currently only used in 5% of the intensively commodity croplands in the US, could be used on a much, much wider scale. And cover cropping, simply putting a crop on the land throughout the wintertime, so that carbon pump is continuing to push CO2 into the ground, is shown to have a significant effect on soil carbon. And that's something that we could do in a policy arena relatively smoothly. So what we showed in this analysis is that we can remove something like 130 million tons of CO2 at a price point of $40 a ton. And if you're willing to pay more, you get more. You get up to close to 1 billion tons of removals by the time you're at 2050. The key thing I want you to take away is that what are we willing to pay? A farmer doesn't store carbon in their soil unless they get paid, just like someone who's injecting CO2 deep within a geologic reservoir gets paid with a 45Q credit. Yeah. Next, I'll just briefly mention forestry, which could be an enormous opportunity in Pennsylvania, 60% of the state being forest cover. We have enormous opportunities to do better forest management all across the US. The particular strategy depends if you're in the Northeast or the Southeast or the West, where I currently live. If we're mitigating fire risk, it's a different answer than we're here in Pennsylvania. Pennsylvania has enormous forest residues that could be used for biomass carbon removal and storage. But all told, across the US, we have an opportunity to remove over 1 billion tons of CO2 and do that at a really quite affordable cost. But what I want to emphasize is it's not just about storing carbon in trees. It's actually about using the removed biomass from those forests, which makes them healthier in many, many cases, and thinking about that waste product, not just for what are the electrons it gives us when we burn it, but what are the useful products that we can make? How can we think about that biomass as a form of CO2 removal? So in the state of California, there's CO2 removal opportunities in using forest biomass all across the state. That's the big answer. But there's also a lot of municipal waste, particularly in the big cities, like where we are right now. And that waste can be used in many, many ways. We looked at 27 different processing pathways. I will not walk you through them all, but we looked at where we have the opportunity to gasify to hydrogen, where we can make polyethylene, where we can make biochar, bio-oil, even asphalt. And across the United States, almost every single state has a real opportunity to do this. Again, the specific technology and conversion might depend on what particular type of biomass is available. But we've got something like 700 to 900 million tons per year of opportunity simply in better using this biomass, which in almost all cases is simply allowed to decompose and is released back to the atmosphere as either methane from a landfill or CO2. And when our team did the analysis of where would the facilities need to be across the United States to optimize the amount of transport and processing costs, they're all across the United States. There are something like 300 new facilities. That is not a trivial number. I think these each cost something on the order of $500 million. But this is what it would need to look like if we want to minimize the number of pipelines and the cost of moving biomass and CO2 around. We tried to localize these near places where we have good geologic storage. But again, we need to move quickly in this space, and it's right now a space that I think is lagging. We need to think about what are the capital investments and how to encourage those to create these facilities and really jumpstart this industry. As I mentioned, the costs for putting up each individual facility are substantial, and not just in dollars, but in regulatory hurdles. I want to spend the last couple minutes emphasizing how important direct air capture is to this story as well. We know how to do this now. We know how to build machines to clean the air, to pull CO2 out of the atmosphere. This facility at Climeworks, you've probably seen this picture a million times. This is one of the original facilities, but we now have facilities across the United States. Many of these are have investments from the Department of Energy and pilot projects. I'll point to Heirloom in particular, only because Noah's here with us, and we're excited about learning that expertise that they've learned. But not just thinking about using that captured CO2 and storing it in a geological formation, but what can we do in the near term before we have the permits for a Class 6 well, and perhaps in using that CO2 for building materials like cement. The last thing I'll just talk about is we did an analysis of geologic storage, because that is the long-term permanent goal for a lot of the CO2. And it is not evenly distributed across the country where we can store CO2. Obviously, we have greater opportunities here in Pennsylvania than in many, many other places. This is one of the top states in the nation for geologic storage. And you have a couple of DOE-funded projects. I'll particularly point to the one that's on the border with Ohio, where you have projects that are in a very mature state of applying and collecting data to get a Class 6 permit. Our analysis included a study of both the energy and the equity and the environmental justice elements of all of those different CDR technologies. Again, I don't have time to go through all of these details, but we looked at who benefits. How does water and air pollution change or improve when we apply these technologies? And I'll just point to the fact that we have benefits that range from social vulnerability, from soil erosion, from the forever chemicals in our soils, that we can really look at these trade-offs across our application of carbon dioxide removal technologies in the US. So as I wrap up, I'll just point to the fact that as Jen and others have made the point that there's a different answer depending on where you live. The different answer for here in Pennsylvania than there is in California. There's no one size fits all. We have to think about the local resources, which is again why we felt it was so important to collect data at the county level. But I want to end where I started with this slide about importance of acting right now and that later is too late. I'm going to just lift the hood on this figure a little bit for you. This is perhaps now, in my mind, the most important figure we published. And what did we use? Excel. These are dotted lines on how fast we'll be able to ramp up the direct air capture and BiCRS, their more technological solutions. And we really just had to make a guess on how fast we can do that because we don't have that data. And I would suggest that that is what your job is today, is to start talk about how do we make sure we are acting on this now so that those curves look at least that steep, if not steeper, and we start to make real movement towards both the capital investment, the policy arena, the regulatory, the measurement arena that allows this kind of ramp up to happen because we desperately need it. So thanks again to my team and thanks for listening.
Any questions
I think
for?
one or two questions? We're probably a couple minutes behind, but yes, please.
Okay.
Yeah.
Thanks so much for your presentation. I'd be interested in learning more about forest management practices. We hear news stories all the time about horrible forest fires happening. Could you share a little bit more about what are these practices that we could start applying?
Sure. So again, I'll just reemphasize that they're different in New England than they are in the West. I'm going to talk first about the West because that's an easy one to think about. A forest is healthier when the West when it has less trees per acre. Because not only does it have less risk of forest fire, but the beetle outbreaks and various pests. Trees are also just designed in the Western US to grow faster and to put on more biomass when they're spread apart. And that's what you learn in silviculture when you first take that. It's also true in New England, but we have a forest that has been degrading for the past 80 to 100 years and is continuing to, but needs to have a certain amount of thinning again to actually put on the pounds in the same rate year on year. So it's counterintuitive, but actually thinning and managing forest allows them to sequester carbon in a more secure way for longer periods of time. In the southeastern US, we're actually talking about agriculture of trees. We're talking about 20 to 30 year rotation forestry, and that's been practiced for some time, but there are a lot of lands where it's kind of fallen out of favor because there's not a demand for those wood products.
Great. We have an online question here that I'll bring in. So you have published a one-of-a-kind report on carbon removal, covering a lot of strategies, but you've also mentioned some strategies that you guys didn't cover, potential strategies that might be important but may not have been included due to lack of cost estimates or other required data sets. So this is a two-part question. One, what is the plan on expanding the research for a more comprehensive list of potential technologies, if any? And are there any technologies not covered in the report that you, and I closed it by accident, one Okay.
that I'm particularly excited about.
That you personally view as important as those technologies that were addressed, even though there's a lack of data
Right.
availability.
Right. Okay. So let me first just say that if you look at the amount of CDR that has happened worldwide, you can look at that at cdrfyi.com, I believe. The biggest answer globally right now is biochar. Did I say anything about biochar? No, because in the United States, it's not being applied at a widespread enough level that we felt we had reliable data to work with. It is a common byproduct of any kind of biomass processing, whether it's gasification or fermentation, and pyrolysis of wood products to make biochar is a fairly straightforward technology. I would love to see that ramped up in the US. It's a great soil carbon amendment. It has all sorts of beneficial effects for agriculture. I'm going to mention another soily one. Forgive me, that's my background. But what we call enhanced rock weathering, or using crushed basalts or other ultramafic rocks, and spreading those on fields just the way we currently spread lime, can have geochemical reactions with the atmosphere that pulls CO2 down. It's actually not always necessarily stored in the soil as some kind of carbonate, but enters the hydrologic system, and we get a net flux of CO2 from the atmosphere through the soil into our waterways. That can also have benefits for growing crops. But those are just two that I am particularly keen on because they can be spread across a large amount of land area. There are new advancements in the sorbents and solvents that are used in direct air capture that I will think make a big difference in bringing down the cost curve. I think that finding ways of doing biomass processing that interdigitate with current facilities so we don't have to put up a whole new plant are also not far away on the horizon. And if my colleague David Ho were here, he would say, well, why are you ignoring the oceans? And yes, we cannot ignore the oceans. I think the area in electrolysis and in looking at marine carbon dioxide removal is very exciting. I know that Roger has just recently been involved in really pushing exploration of that space. It's obviously a huge opportunity, but there's a lot we don't know. So again, from sticking with my mantra of not waiting, I think that there are some of those spaces that we could start working on immediately and some that will take some years.